Everyone, let's make a start. So hi to all of you. Good morning, good afternoon, or good evening, depending on where in the world you're joining us from today. It's really nice to see so many people here. Quick intro, I'm Rose Pritchard. I'm a Presidential Fellow in the Global Development Institute at the University of Manchester. And I work broadly on questions around forest change and rural livelihoods. And I've got a particular interest in uses of satellite Earth observation data for development. So that's the motivation for my interest in our theme today, which is all about how could big environmental data shape the futures of forest landscapes. And we can debate what big environmental data are in the discussion later, if that's what you all decide would be fun. But broadly, we're thinking about these newer data sources like satellite remote sensing and other kinds of remote sensing, new sensors which can be used for things like camera trapping or bioacoustics, the rise of citizen science, kind of enabled by the spread of mobile technology. So this kind of fresh abundance of data that we have on a lot of rural landscapes, coupled with improved computational power and improved analytical like techniques and methods, and those things in tandem mean that we can answer questions now which just wouldn't have been possible in the past. And as someone who trained as an ecologist, I find this very exciting. But as someone who's moved into the environmental social sciences, I can also see all of the questions and challenges this raises, particularly in terms of what this could mean for the people who live in rural landscapes, for rural livelihoods, and for rural well-being. And luckily, we have 4 brilliant panelists who are going to help us explore those ideas today. And we're particularly lucky because we have panelists who approach this from a lot of different perspectives. So we have people who are more focused on the kinds of technical methods sides of things. We also have people looking at this from livelihoods and from political ecology perspectives. So it should be a really good conversation. So in terms of the structure of our session today, we're going to start with those 4 presentations, and each of our presenters will talk for about 10 minutes each. And then we're going to go into a discussion. And I know that there is so much expertise in our audience today. So the idea is that that will be very much a conversation. It's a chance to share your own perspectives as well as to ask questions to our panelists, to our presenters. So a couple of bits of housekeeping before we jump into the presentations. We'll ask that we'll keep all questions until after all 4 panelists have spoken, but please do put your questions in the chat. We'll keep a track of those as we go along, and we'll come back to them when we get to the discussion stage of the webinar. And also, we are recording the session today, so if you'd prefer not to be on that recording, please feel free to keep your camera off. And if you'd like to ask a question anonymously, you can send that directly to me in the chat, and just to make a note that you want to ask without your name attached to it, that's totally fine. Okay, so I will hand on to our first presenter. So that's Johan Oldekop, who is a senior lecturer at the Global Development Institute at the University of Manchester. And he's going to talk about some of the fascinating work he's been doing recently, bringing together different data sets to understand links between forest change and rural livelihoods. So Johan, it's all yours.
Thanks, Rose, and thank you, everybody. I'm really excited. This is my second webinar, so it's all still really new to me, and it's also so nice to see so many faces here. Some of them familiar, close colleagues and friends, and I'm really sorry that we can't do this in person. It would have been really nice to see you all. I also want to apologize in advance. I've been on Zoom calls all day and my voice is a little bit hoarse. So if I go into a coughing fit, I've got a little bit of water and I'm going to try and mute myself as quick as I can. So I apologize in advance. You should be able to see my screen. Yeah. Okay, great. So I'm going to maximize this and then hopefully you can see everything. Okay. So my name is Johan Oldekop. I'm based at the Global Development Institute. I'm a biologist by training, and I've become, I guess, increasingly interested in trying to understand what works for conservation. So that's the kind of angle that I've kind of approached this from. And over the last 7 years or so, I've been kind of increasingly interested in how we can combine different data sets. Partly that's a frustration that came out of my PhD, where I felt I didn't collect enough data. And partly it's also because there's been this huge amount of data that's become available, and so how can we use it to try and understand intractable problems? Most of my work focuses on forests and livelihoods, so that the people that live in areas that are covered by forests or trees. And I'm going to be talking a little bit about some of the thinking that I've been doing around this over the past few years, and present some of the work that we've been doing. So why focus on forests and livelihoods? So why is this area important, and why am I interested in it? So globally, there are about 1.6 billion people that live within 5 kilometers of a forest, and approximately 65% of these live in tropical countries. So there's a huge part of the global population that depends on these forests for part of their livelihoods, and who are also stakeholders in the decisions that are made about how to protect and manage these natural resources for conservation or for natural resource management in terms of livelihoods. We're also seeing really big changes in forest landscapes. So this is some work that Laura Wang Rasmussen, who's also on the call, I saw did with me, and a bunch of other people. And we're basically seeing a huge array of changes in forest landscapes. So this includes kind of big disturbances in forests from kind of ecological terms. So we're seeing big tree mortality and these big wildfires. The ones in California, for me, are particularly striking. We're also seeing really big shifts in rural populations. So rural populations, or kind of large proportion of rural populations, are migrating to urban destinations. So that the landscapes, the human aspects of these landscapes, are changing dramatically. We're also seeing huge investments in rural landscapes through big kind of agricultural production systems. And we're also seeing a huge advancement and kind of development of information and communication technologies, right? So the way in which we can access and make use of data is really changing dramatically, and it's changed dramatically since I started working on this for my PhD. So I would say that most of the work on research, most of the research on forests and livelihoods that's been done, I guess from my perspective, has deeply been influenced by the work that Eleanor Ostrom and colleagues did around trying to understand what works for local communities in terms of the kinds of institutions and management regimes that are set up to try and manage these forest landscapes in more sustainable and more equitable ways. But I think there's also been some limitations around some of that work. So when we look at much of the work on forests and livelihoods, we find that it's generally either focused on the forest aspects or focused on the livelihoods aspects. So this is what Arun Agrawal and Ashwini Chatre term monoconsequentialism in one of their papers in Global Environmental Change. And that means that we have kind of relatively little information about joint outcomes and trade-offs. We often talk about these joint outcomes and trade-offs, but we actually have, I think, relatively kind of hard data on how these things pan out in tandem. My feeling is also that we've focused on individual drivers of change in studies. So we tend to focus on only one driver when we know that in fact these forest landscapes are really complex, and you often have kind of multiple drivers kind of operating simultaneously. And so that's a term that to kind of follow Arun Agrawal and Ashwini Chatre's term, kind of we defined as monodeterminism. So we know little about the relative effects and interactions of forest sector interventions. And finally, we've had these very big kind of forest and livelihoods kind of research programs, the IFRI network, the the Penn study that C4 did, the Sentinel Landscapes program that C4 and ICREF did. But they've been, I think, hampered by low-powered statistics, sample sizes, and also lack of longitudinal studies, right? So we tend to only focus at one particular period of time. And so what that means is that we have relatively little information about what works. So the ability to make causal inferences about particular interventions or combinations of interventions, I think, is relatively scant. And because we don't have these kind of large spatial overviews over time, we also don't necessarily have the temporal or an understanding of the temporal and spatial heterogeneity. So we don't often know why particular interventions work in some places but not in others, or when they work, right? So the kind of temporal resolution there is something that we don't have a lot of. So kind of the amount of data that's become available is helping us, I think, to try and understand this a little bit better. And I became really interested in how we can combine the kind of availability of relatively off-the-shelf products that look at land cover change with off-the-shelf products that include kind of information on livelihoods and interventions and kind of demographic, social, economic factors. And I want to highlight some work that Cecilia Dingeland did. She did her PhD with me and Carl Evans at the University of Sheffield. And she essentially tried to understand the role of social protection programs and how they affected multiple social and environmental kind of aspects in Brazil. And she did an absolutely amazing job at trying to collate data from multiple sources. So the part that I want to focus here is working on this PRONAF modality, which is essentially a low interest rural credit program that enables kind of small scale farmers in Brazil to kind of diversify and expand their agricultural production. So the map that I'm showing here is the kind of spending that you see as part of this particular program. So as part of her PhD, she compiled a huge data set of kind of from multiple sources, which kind of linked to some of the kind of sustainable development outcomes. So looking at poverty, food security, and life on land or land use change, and then trying to link that with investment in this social protection program, and then a whole series of different kind of data sources, again, which come from public sources. And she was able to compile this at the level of municipalities for about 4,000 municipalities, rural municipalities in Brazil. So it provides this kind of edge-to-edge analysis of multiple outcomes, which allows us to look at how these things change over time and how they're spatially heterogeneous. And that's what I'm showing you in this slide, right? So this is looking at the way in which this particular social protection program has influenced multidimensional poverty, kind of food security measures in terms of protein production, and also natural vegetation change. And one of the things that comes from this is that you can see clear areas where some of these policies, or in this case, this particular policy, have led to kind of joint positive outcomes for the environment and people. Sorry. And also areas where you see potential trade-offs. And so one of the things that these kind of big data analyses, and I'm including kind of census data, which might not necessarily be technically big data, but can be linked to big data, allows us to understand or identify areas or regions where we might be able to find out why particular things work or why they haven't worked. So I think there still remain a number of challenges. So data oases and data deserts, and this is a term that Dan Brockington used and which I have co-opted because I think it's brilliant. And there's a question here about how do we fill these data gaps? And I think some of the work that's been trying to link remote sensing data with national census data or representative household surveys to try and use remote sensing data to predict kind of poverty and essentially fill the gaps in representative household surveys is really exciting. So I think at the moment we're relatively good at trying to predict individual moments in time, and the next challenge is to look at changes over time. And that's something that I think hasn't worked that well yet. And Bowie Den Braber, who has done some work on this, I'm curious to know what he's thinking. The other thing that's really changed is the ease of integration into other analyses. When I started, Google Earth Engine didn't exist, and now it dominates. So how can we make it use these tools to our advantage? Sorry. And finally, how can we make these data more democratic? So whose data for whom? So Global Forest Watch has made some of these data much more easily available. But how can we make sure that these data actually are used by the people that might be able to leverage them in order to address kind of social justice issues? And I'm going to stop there. So yeah, thank you.
Great, thank you very much, Johan. That was all really interesting. So as I said, we're going to do all the presentations and then have questions at the end. So our second speaker is going to be Keiko Nomura. And Keiko is a senior analyst at Space Intelligence, which is a geospatial consultancy based in Scotland, who are doing really interesting work on forest change. And as you can see, Keiko is going to talk about uses of satellite data and artificial intelligence in scaling up forest monitoring and conservation. Okay, Keiko.
Thank you, Rose. Hello, everyone. Thanks for the introduction. My name is Keiko Nomura. I work for a company called Space Intelligence. So I'm a little bit different from other speakers coming from academia. So I hope to give you some industry perspective to this meeting. The title is, as you can see, about the use of satellite and AI. So here, big data, I mean satellite images, and I focus on possibilities and challenges using such big data from a little bit more technical perspective, but focused on application. Oops. Before going into the content, I just want to talk briefly about the company. Space Intelligence is a startup company based in Edinburgh, Scotland. It was founded a few years ago, now 3 years ago, by Dr. Murray Collins and Professor Edward Mitchell from the University of Edinburgh. We use satellite data and translate them into information that can be used for making environmental decisions. And about last year, this time last year, we were awarded to develop AI-enabled technology to address climate change emergency through a fund administered by Scottish Enterprise. And using that fund, we worked with Nature Scot and Scottish Wildlife, and we classified and created maps of Scotland land cover. But routinely, we provide biomass mapping, peat condition mapping, and other types of vegetation mapping, such as forest. And why satellite data? Well, now, not exactly today, but about a year ago, there are about 2,666 satellites are operating and orbiting this planet, and among which 446 are for Earth observation. So you can imagine a lot of satellite orbiting and basically providing information from there. And just to give you a little bit more insight, a little more than half is a commercial satellites and followed by government-owned satellites for 16%. it's important to just briefly explain there are two types of satellite sensors, passive and active. So passive sensors detect natural radiation like reflected sunlight, as you can see the sun in the image on the left, while active sensors use transmit signals like microwave radar or laser and receive the radiation that is reflected or backscattered on the object. So for passive sensors, it looks like very familiar images that we see on our phones and cameras, while images from active sensors, this is from SAR, synthetic radar aperture from Sentinel-1, it looks different because it's capturing very different physical properties of the object, and it's simply visualizing what it's backscattered. But one other thing you noticed among two images is the presence of the cloud in the optical image. So radar can penetrate the cloud, so it's very advantageous in that regard, while optical is obstructed by cloud. At the same time, today, taking out of the cloud is a common practice using this big data. You basically create a synthetic mosaic image of the area using from different dates, and you just take the cloud out and then create the mosaic. So it's a cloud-free images. Now, one other data set I wanted to stress is JEDI data. This is a LiDAR sensor, light detection and ranging. So this uses a laser beam pulse to measure the distance of object by using the speed of light. And NASA's Global Ecosystem Dynamics Investigation, it's JEDI, it's very good for, it's capturing information about canopy height and cover and the ground elevation levels and so on. So in a way, it's like a 3D image of the Earth, but not exactly, because if you pay attention to the lower left image, JEDI orbital coverage, you see the white lines going around the Earth. So that's the JEDI orbit path. It's attached to the International Space Station. So it doesn't have its own satellite, but it's going through routinely now. And it's a transect data. So it's not wall-to-wall image of these 3D information. But as you can see, within the first 2 months, the gaps between these white lines are already being filled. So by the end of this mission, which is, I believe, 2022, massive amount of data will be collected. It's expected to be 10 billion observations. So this is going to be a really important data we could take advantage of for monitoring forest and other types of vegetation. You can see that on top of the Earth is empty there. It's not covering the boreal forest, but it does cover tropics. So more than probably hundreds of terabytes of data collected every day at global scale. And the table shows commonly used satellite for forest monitoring, but you see the revisit column. The Sentinel-2 have 5-day revisits, and then the Planet program has a monthly mosaic. So the frequency of these satellite images are quite high, and it enables up-to-date and in situ measurement of the area of interest. So the big data, big possibilities, a lot of exciting things can happen. But as I said, so there's different types of sensors. We can capture a lot of different information at the global scale, and then also at temporal scale. We can keep getting these information going forward, and even going back, Landsat program goes back to 1970s. So there's a massive amount of data currently we have at our hand. Even those are freely available satellite images. So how do we translate such big data into information that's useful to us? This is where AI, artificial intelligence, comes in, because AI is very data hungry and it's very good at dealing with a lot of data and finding patterns within. Human intelligence has limitations as to how much data we can handle, but AI loves more. More data they have, the better they can do with it, usually. So this is a very big general workflow using AI and predict information we are looking for. So we use training data, which is basically labeled data on the ground using our knowledge, and then satellite images go into overlay with the training data, and we train the algorithm to predict the information we want them to. And then at the same time, you will do some testing internally, which is separated from training data. But ideally, you want to do very independent validation by using very different data and a different group of people. So what can we really do with big data and AI? So here are a few examples from our previous project at Space Intelligence. On the left, it's a biomass mapping at Madagascar. On the right, this is with Scottish Wildlife Trust. They were interested in seeing tree connectivity along the river. So you can see easily about the scale of this kind of analysis and how it makes sense to use satellite data. Now, our most recent project, which we just finalized, is the land cover map of Scotland for the last 2 years. This is with NatureScot, and the NatureScot estimate every year natural capital asset index. And in order to do that, they use land cover information based on UNIS level 2 habitat class. UNIS is a harmonized European classification system. And there's an example I put here, that A, B, C, D. And so that's the level 1. So it's a hierarchical classification. So as it goes into more detail, there's the level 2. For example, D1, raised and blanket bogs, D2, Valley Myers, and so on. So you can imagine the level of detail at level 2. So this end up, basically, we classified Scotland into 22 different habitat classes, and many of them are visibly quite similar. So we started with Cairngorms National Park, which is the biggest national park in the UK. And after we tested that, we moved on to the entire Scotland. And this has been recently finished, and it will be available at the government data website. And as you can imagine, this is very easy to update every year. You can repeat using same methodology, and you can capture the changes very effectively. And you can also use this as an opportunity to identify where to restore for different type of vegetation, like wetland or peatland. So on the final thoughts about big data, possibilities and challenges, as I stressed, it's a massive amount of data, not just spatially and spectrally, but also the time scale. And more data are really coming from the space. So that means you need a big platform to process it. And the cloud platform has become quite a norm now. It makes sense to use cloud. At the same time, you can also focus on what you are really trying to get out of it and do it more smartly. Maybe you don't need high dimensionality in data. Maybe you need some one smart indicator that can answer your question. So always it's good to bring your focus back to what you are trying to do. And the second point, training. Here by training, I mean ground truthing. So as I showed you the workflow, AI algorithm is as good as what we train with. They can't predict what we didn't train them for. So we do need a lot of labeled data, and good quality labeled data. As pure as the polygons are, the better. That requires actually a lot of knowledge on the ground from local communities and from experts. In case of Scottish land cover map, we worked closely with botanists from NatureScot, for example, and using more cool tools, you can also take advantage of like active learning or some ways to improve the training data. And there are several solutions to deal with imbalanced training data as well. And more satellite will be launched and more data will be coming. So that means more labeling will be required, and we have to keep learning. And doing so, especially on the point of training data, when the users use the map that's been predicted and they validate the data, we also envision this system to feed back to our modeling. So we could use the data validated and use for the next round of prediction. This will definitely help getting more training and a better and up-to-date training data. So in summary, more and bigger the data is, actually more human effort and intelligence would be required. But the possibilities that we can do with big data is extremely exciting, with much higher accuracy and lower uncertainty in the future. That's my presentation. Thank you very much.
Thank you, Keiko. That was great. And it's so nice to learn more about your work. Also, your graphics are amazing. So now we're going to have a slightly different perspective because we're going to hear from Laura Sauls. So Laura is a Leverhulme Early Career Fellow in the Department of Geography at the University of Sheffield. And she's going to talk about how the increasing use of these kinds of data does sometimes make it harder for community voices to be heard, but also now how communities are using these data themselves to come back into those debates again. So Laura, it's over to you.
Thank you so much to Rose for this invitation. And as she said, I'm in the Department of Geography at the University of Sheffield. And I guess I'm returning the favor since Rose spoke at a webinar for us yesterday. So I'm going to speak a little bit to that provocation that Johan ended with. And also, I really appreciate that Keiko gave us a good look at kind of the scale of big data availability for us. So for context, I engage in some remote sensing and GIS analysis in my research, but and I do a lot of collaborations with people who identify as remote sensors. But I primarily do qualitative research, and I primarily do it in Central America. So reflecting on my experiences, both in these collaborative workspaces and also my experiences, I wanted to speak a little bit to three kind of provocations, if I can get this to advance. So I'd like to make three kind of main points today. And the first is that big data is ubiquitous, but always partial. And I guess I should say these points may be pretty obvious, but I feel like sometimes we don't say the obvious out loud, and that leads us to make assumptions about what we mean and what we're trying to do. So I want to kind of restate some of these points and maybe think through them from the cases I worked with before. All right, so first one, big data is ubiquitous, but also partial. Environmental big data is never neutral. And third, environmental big data may promote inclusivity in forest governance, but it can also be the basis for exclusion. So when big data is ubiquitous, but also partial, I mean, there's so much data with such amazing coverage of the Earth's surface, but it can only provide us with snapshots of what's going on. And even, planet data, something that's so fine scale, can't capture information about human relations to the environment in some of the things that are necessary for thinking through forest governance. When I say environmental big data is never neutral, I mean that the technologies that we use and the type of data that these technologies generate are situated. They come out of a certain tradition of knowledge production, and they're oriented towards what their designers see as problems that are worthy of investigation, and that leads them to focus their eye in certain places. And when I say that environmental big data may promote inclusivity, but also could be the basis for exclusion, I'm kind of following on from points 1 and 2. to say that the generation and use of environmental big data can be used just as easily to exclude vulnerable or marginalized peoples from forests as to promote their inclusion in decision-making around those spaces. So I guess it's important to ask the question at all times, does this work lead to the possibilities for greater inclusion? There we go. So there are just such great volumes of data out there, and Johan showed a little clip from the Global Forest Watch site as well, and I wanted to pull up northern Guatemala, where I work and where I'm going to kind of speak from a little bit today. So that ongoing passive and active collection of data means that there is data everywhere, and there is data for everywhere. Right? So we are surrounded, we are generating data every time we're sending an email or logging onto Facebook. We are tuned in to these kinds of environmental big data as people who are interested in, for example, deforestation, forest restoration, etc. And we're collecting so much data that and more is coming online, as Keiko just said. And I'm really glad that she covered kind of how everywhere data is, because I was going to give an example from Landsat that's not nearly as interesting. So the proliferation of not just data, but ways to access data and the availability of it means that there's kind of opportunities to explore these environmental topics for almost every part of the world, especially when we're thinking about deforestation. And we literally have data about everywhere. But even though the amount of data that we have and its broad coverage means that we have a lot to work with when we're trying to explain what's happening on the Earth's surface, we really can't capture all of the factors that are in play in a given place. So we know from experience what different drivers might lead to deforestation. And with more and more data coming online, we're able to take advantage of remotely sensed ways of, for example, tracking the agricultural frontier or identifying where mining or infrastructure is leading to knock-on deforestation. We're able to see patterns in how small-scale charcoal production, how that looks in a forest. So we're able to kind of see a lot of what is happening, but we don't always have a way from the remotely sensed data. And I think Johan captured this in some ways too, by highlighting that disconnect between data on forests versus data on livelihoods. We don't necessarily know, for example, why these drivers affect deforestation, where they do, and how. And we also don't necessarily then turn our eye to what is happening in landscapes that aren't experiencing deforestation. So we can describe the what and sometimes the how, and very occasionally the why when we're thinking about remote sensing and geospatial big data and deforestation. But we often miss out on thinking about the meaning and kind of the implications for policy unless we are thinking about other types of data as well. So I would say data is everywhere, but always partial, because just as any other form of data collection, it is coming from a specific set of interests and captures a specific set of phenomena. So moving on, when I say that big data is never neutral, I'm thinking that from conceptualization to analysis to dissemination, the production and use of environmental big data, especially geospatial data, is embedded in existing institutions and structures of power. And it reflects certain values, both around what matters, like what is the environment and the environmental problem of concern, and also questions around what knowledge looks like. And I'm pulling here quite obviously from a lot of science and technology studies and some feminist critiques of science, but I think it's worth thinking about in terms of thinking about environmental big data in the context of knowledge production and knowing that in the realm of policy, certain types of knowledge still matters more. So kind of thinking back to Donna Haraway, who talks about this view from nowhere of the satellite as a God trick, where we're assuming some kind of objectivity or a non-situated nature of knowledge once we're collecting data from up in the atmosphere. And we know that there might be errors in classification. We might recognize that we need image correction because of cloud cover and things like that. But there's still kind of an underlying assumption in a lot of geospatial data collection that we are capturing what is truth, what is on the ground. And I think there's something to be said for we are capturing that snapshot of the thing that we are looking for, what our eye is trained on. But that God trick misses out on the relations between people, the relations between people and environment. And perhaps even more importantly, can even obscure politics. So these are 3 maps of that part of northern Guatemala. And the one on the right, I don't know if my mouse shows up or not, but the one on the right, there's a red outline, and that is the proposed Mirador Wildlife Reserve within the Maya Biosphere Reserve, which is a man in the biosphere reserve. So there are areas that are under strict protection, areas that are multi-use or under protection, but communities are allowed to use, and then a buffer zone. And this proposal by an American archaeologist, or a group led by an American archaeologist, would turn the area highlighted in red here and in yellow here into a strictly protected wildlife area where only conservation and heritage tourism activities could take place. And this, of course, is not necessarily in the interests of the communities who are already working in this area. So these communities are in this map in this green color, over here, over here. And in this map, we made them in dark green. And I say we because I actually made this map along with my partners in the Association of Forest Communities of Patan, or ACOFOP. And both of the maps on the left are using data from NASA's FIRMS portal, which is the active fires data. So this is MODIS and VIIRS satellites, and it's supposed to be basically showing anomalous hotspots in the region. And in most of the cases in this area, anomalous hotspots represent fires. So this is the same data mapped in slightly different ways. And I bring this up here as an example of kind of the non-neutrality of this data, because how we map the data, what borders we use, the colors and the size that we use, the cartographic representation of this data has huge implications in political disputes over who has a right to be in a forest. So in this top map made by the American Archaeologists NGO, they have layered 12 years of fires on top of each other, and they've called it slash and burn fires, right? And they also don't demarcate any of the community versus non-community land uses. So what we've done down here, which is still a political act, is try and highlight where the fires are versus where they are not based on community management versus public or private management of land. And as you can see, it looks like visually, there's a lot fewer fires in these dark green areas, which are the community lands. And we did some like very low level statistics, as Johan would say, and that's what it also suggests. But both of these, using the same data, both of these maps are entering into the public sphere, and they can have they kind of demonstrate that how that data works in practice has a very different implication based on who is using the data. Moving on to this question of inclusion or exclusion, and I know I'm running up against time, Rose, sorry. I wanted to highlight that the types of knowledge that are valid in debates over policy are often related to questions of who can access data, who can use it, and also which knowledge is valid. So I just want to make the case that the rise of environmental big data provides new opportunities for forest governance that is more inclusive of local communities, but that this pathway can also be constraining. And perhaps requires us to give up other ways of thinking about expertise, about environmental trends in a given place. So this photo is part of the Oldekop group from Guatemala, and they were being trained on drones. And there's a trend, especially in Latin America, of community, I think in Indonesia as well, of community forestry groups increasingly using drones and GIS software, pairing it with data that's publicly accessible, like that firm's data set, to generate their own data about forest fires, deforestation, and threats. And by entering this kind of expertise, this Western technological knowledge into conversations with donors, with the government, they're able to make claims about their effectiveness as environmental stewards that can be externally validated. But I kind of question to what degree this focus on spatial data might erode some of the types of more qualitative or relational data that these groups have historically relied upon to understand what is happening in the ecosystems that they depend upon. And it also, when we have a view that's so removed from the experience on the ground, we're in some ways able to suggest that these folks don't need to take on so many threats, but they do, in fact, go and confront problems with narco trafficking, illegal cattle ranching, oil and gas production. And there are really these folks are taking risks every day when it comes to thinking about environmental threats, and to what degree are our governance systems including and recognizing and validating the risks that they take on. So Oldekop is a pretty tech savvy group, and I would also argue that for groups that aren't as savvy as Oldekop or don't have as regular access to electricity and mobile data, for those who are not able to start engaging in these types of data production, perhaps it is another source for exclusion if they can't provide this kind of geospatial data and input it into political claims making processes. All right, so I am getting to the end, I promise. I'm gonna totally just mix metaphors and cliches here. The first is the idea that a picture is worth 1,000 words, right? A map is a picture, it's a way of representing the world. And in policy spheres, especially around things like deforestation, maps have become absolutely essential to both understanding and describing the problem, but also to capturing imaginations about threats and possibilities. And so these pictures can both create opportunities for forest communities and foreclose them. And because of the power of these data and the ways that they are represented, I'm going to parrot Spider-Man and say, with great power comes great responsibility, right? So when we're thinking about geospatial data represented cartographically or analyses that are policy oriented, these are phenomenally powerful when it comes to shaping the conversations around forest governance. So those of us who are really trying to work on questions of deforestation and its perverse impacts, including on local communities, it behooves us to stay attuned to these questions of power and access, and including perhaps rethinking our responsibilities around questions of collection, analysis, and use, and also who we're trying to speak to via our representation of environmental big data. So I think environmental big data can help us to identify problems, ask better questions, and also gives us an opportunity to work with other types of data and to think about forests and governance in the place that forests are. So to place our big data back into the explicit political context and lived experiences of those in forests. And I'm hoping that's where the big possibilities come from. So thank you, especially to Rose and to all of you for your patience. And yeah, that's Thank you.
Great, thank you, Laura. So our last speaker today is going to be Polyanna Bispo, and Polyanna is a lecturer in the Department of Geography here at the University of Manchester, and she's going to talk a bit about Earth observation and data integration for forest structure estimation in the tropics. Now, Polyanna, just before you start, if people could start adding their questions to the chat while Polyanna is talking, and then we can get going with the discussion straight after.
Just let me try to. Can everybody see my screen? Yeah? Okay. Thank you, Rosie, for the invitation. Thank you for Johan, Laura, and Keiko as well for the nice presentations before mine. And what I'm going to present here kind of will go through all the three presentations, especially the presentation from Keiko, showing a little bit more technical things related to big data and Earth observation. So when I was thinking about the preparation for this webinar and thinking about how could environmental big data shape the future of forest landscapes, I was thinking, okay, I will gonna try to focus a little bit more in the work that I do in tropical forests and how the big data are helping me, for example, to cover some of the challenges related to uncertainties to estimate forest structure and in the tropics. So I'm going to focus on the Earth observation data integration, as Rose mentioned before. So I am someone that uses field inventories and different types of remote sensing data sets, the passive remote sensing or active remote sensing as well. And I try to integrate all this information through spatial analysis using cloud computing that Keiko already mentioned, explained before, to understand biodiversity, dynamics and forest structure and carbon stocks. Okay, so my main study area of interest is the Brazilian Amazon and Brazilian savanna or cerrado. As you can see here, you can see this, they are the biggest areas, biggest biomes over Brazil. And then you have this transition area between Amazon and Cerrado that is most of the time, it's a line divided both biomes used by decision makers. And sometimes we lose this idea of ecotone, that is this region between both. And it's the area, the transition between Amazon and Cerrado is one of the areas where we're having the most deforestation happening in the last 10 years, is where we have this, oh, the light's coming, where we have this kind of, how can I say, the expansion of the agricultural and illegal activities through from the Cerrado to the Amazon. And you can see here, using this image, this animation from Global Forest Watch, if you come back to that, and pay attention to the transition between both, you can see in this image this kind of pink areas are where the deforestation is happening, and this is it was from 2001 to 2019. It's quite scary. And if you see in Cerrado is one of the areas where we are suffering a lot by illegal activities and also expansion of agriculture, soya plantation, and everything in Brazil. For you to have an idea, at the moment we have only 3% of the Cerrado is still preserved in conservation unities, only 3%. And we have a lot of endemic species there. I'm focusing in Cerrado here because, I mean, I study Amazon as well, but Cerrado is one of the areas that are suffering the most at the moment. And sometimes it's forgetting because it's the area where the agribusiness are much more, how can I say, is much more important, much more important activity in that region. And why I'm showing this as well is because we have a lot of problems and challenges in tropical areas, as you know. That is the deforestation caused by a series of factors, the drivers that we already was a bit covered before for the other panelists here. Forest degradation, and this leads to the biodiversity loss and carbon loss that has implications in this in our planet as a whole. When you think about climate change, when you think about biodiversity a loss that has a lot of impact in our lives, even if we're not feeling at the moment immediately, we know that's impacting our life now and in the future much more. So I just want to show this figure here that shows the immediate impact and long-term impact when you think about forests. You are seeing here a figure showing a forest, a nice forest, a tropical forest, where you have the complexity preserved, you have the stratification and the complexity, a high biodiversity, and a soil very humid and healthy, where this vegetation can stand and it has a high resilience. And then in the other side, what you see a degraded zone, a degraded area. Yeah? When you think about that map, we can see, for example, the transitions between savanna and Amazon, the deforestation going, the degradation as well, that's not immediate. The deforestation, when you think about clear cut, you cut the forest and you have immediate like that shock. Okay, no tree here anymore. And the forest degradation is a bit more long term, right? You have, for example, a fire happening. You have some trees that survive, but you think that they stand up for some time, but they can die because, as you see in this figure here, what happened is that this forest lose the stratification. You have then, I don't know if you can see my mouse here. You have more wind at the ground. And then, so the edge of the forest is more likely to be disturbed by storms, by strong winds, and you have some mortality of these trees happening, and it gets more trees start to die, not immediately but long term. Then you have a canopy that is much less complex. You have less trees, fewer species, and you have the soil that start to be drier and not be able to sustain this forest anymore. And the long term, this forest will be the trees will be dead. You increase the mortality. Okay, and this is the problem that I'm interested in. And I use then, as Keiko already explained before, but then I use active and passive remote sensing and try to integrate them to understand the forest structure. So we have the optical data sets, that Landsat, for example, that are more sensitive to the chemical and biophysical information of the forest. We have then the radar that's more sensitive to the geometry of the forest, the structure of the forest, the water content. Then we have the LiDAR data sets that's, in general, we have this much more higher resolution data sets, and it can provide a very detailed 3D information of our forest. So we have this powerful advantages and disadvantages in each one of those, but when we combine them, we can be able to improve our estimatives, our monitoring, and also to map the uncertainties, because as Laura mentioned before, we have a lot of uncertainties associated with big data that we need to be aware of. This is only an example of a work that we did using this data integration to map the above ground biomass of an area in Cerrado. So basically, we use the inventory plots, field plots, to calculate the above ground biomass. We extrapolate these plots because it's a challenging in Cerrado. We get field plots. So we got, for example, 15 field plots and representatives of different types of forest types in the Cerrado. We then extrapolate them in an area where we had airborne LiDAR. It was 60 tiles of airborne LiDAR. So we train our algorithm and extrapolate, and then we use this above ground biomass from LiDAR to train our algorithm to using radar and optical data sets to then using machine learning, in our case, random forest, we're able to estimate the first high resolution above ground biomass map of an area in Cerrado. And also we could generate the uncertainty of this. Okay, here's only an image showing this map. On your right-hand side, you have the map, the final map. And I would like to show this as well for you to have an idea how fragmented the area in Cerrado is. For example, the area here in blue is the area where we have bare soil or agriculture. And the areas where we have, it's more like towards higher biomass, right? The areas towards the red or orange are the areas where we have forests, different types of forests in Cerrado, okay? So, and by integrating them, we're able to increase a lot, generate a very detailed map over this area with accuracy of around 90%. And here is only I just want to show you a visual, to have a visual idea what I'm talking about. For example, over that area, we have some global maps that can map and and try to estimate the above ground biomass over, for example, the area in Cerrado. But we have here from B to E different maps, and visually we already can see how that those maps cannot take so much the information and the detail of the biomass or even the forest structure when we compare with A, that is where that is one area that we extracted from the map that is generated. Okay, so integrate that data. It's very important, especially at the moment that is possible to do because we have so much data available. But however, we have problems as well when we cannot rely on okay, we have many data sets, so let's put them in the blender and then we get a nice map at the end. Is what Keiko said. It's very important we have a very good data sets for training, a good ground truth, because the algorithms, they are powerful, but they cannot do anything without your judgment when you select the data sets that you are inputting in your including your algorithms. I just want to show these slides also related to above ground biomass. This was a work that we contributed to generate the above ground biomass, global above ground biomass for 2010. And an interesting thing here when I'm talking about estimatives and uncertainties is that here you see on top the above ground biomass globally, and then here on your right hand side you see the two-side average standard deviation that is related to the uncertainty associated with this map. And you see that the latitudes around the tropical zones is the area where we have the highest standard deviation. So it's very challenging you accurately estimate the biomass of those areas. You have indications, high indications, good indications, but it's very difficult to get a very accurate map. And this is in one time. When you think about a temporal or a change in above ground biomass or carbon stock over time, this is much more challenging because imagine that you add or multiply these uncertainties. So, but we're in the right moment to try to solve this, and there are many scientists already trying to tackle. For instance, there are big projects from ESA, Biomass CCI, and other programs around the world trying to tackle this problem and try to see how we can estimate accurately the changes in biomass over time. So Keiko already mentioned that. So at the moment, we don't talk about satellite images and data. We're talking about constellation of satellites of European Space Agency, constellation of satellites in NASA, JAXA, Japanese Space Agency. So we have many data valuable at the moment, and how we can handle it. Also complement what Keiko said, we can use artificial intelligence, deep learning, machine learning. For instance, here's just an illustration that you can use different types of remote sensing data sets as well as ancillary data sets, for example, demographic data sets, and combine them together using these powerful tools to produce your maps and your estimatives, and also enable you to get uncertainties associated to that. And this makes much more easier to take like ethical decisions about your landscapes. And again, the ground truth, it's very important here. Your judgment as a scientist in order to select the best and the amount of training data that you use for in your algorithm, in your study. Okay, so you are in the right moment where you have a lot of data. We have a lot of tools that can handle those data. That is the artificial intelligence and cloud computing as well. So we have these platforms you can use, for example, Google Earth Engine. That is, I mean, it's at the moment is one of the powerful spaces that we can use to handle these data sets in a way, in a more friendly way. Here's only an example about just to show how powerful it is to use this cloud computing. For example, we generated, this was a work that we contributed with Pedro Rodrigues. He generated a map of above ground biomass of Colombia. And it was like, he managed to run terabytes of data in few hours. So I think it's 1 hour or so, I don't remember at the moment, but it was quite impressive. And also,
I think we're going to have to wrap up, or we're going to run out of time for questions and answers.
Sorry. Okay. Can I just show the last one? This is the last slide, sorry. So I just want you to finish with this kind of research gaps about that related to forest, that with how to reduce the uncertainties in the forest structure and carbon stock using, sorry, I just concentrate here. So how to reduce the uncertainties in the forest structure and carbon stocks estimation, how to calculate these changes in forest structure. And the last one is that I'd like to leave you is how could you use big data for forest restoration, because you can use for deforestation, forest degradation, but how we can use in a better way to support restoration programs in order to support, monitor, and better planning ecosystems and landscapes. So is this, sorry to go further with the time. Thank you.
Great, thank you, Polly, and thank you to all of our speakers today.